So, what I was going to talk about today is really what's happened, looking back in the last 12 months, 2017 through now, what's happened in the state estimation area, bug fixes, feature. Yes?
The camera's right there.
Oh, the camera's right there, sorry. I'll talk from behind this. So, I just wanted to cover the what we've completed, what are still the open issues, and then some of the items for development for the next 12 months. And not wanting to sound repetitive again, but thank you, ELAB, for your support. Most of the EKF work last year was a result of ELAB sponsorship. So we've got 5 features went in, bug fixes, there were numerous small fixes that went in and some minor enhancements. We've got some open issues, a couple of, only 2 of them are bugs, 22 others are really things where people would like the EKF to do something a bit different, but it doesn't. Or it's an interfacing issue between the EKF and other subsystems. Okay. Now, before I go any further, there's still a little bit of confusion out there about what's EKF2, what's EKF3, who should use EKF2, who should use EKF3. Okay, EKF2, SA default estimator, it's got 23 states. And it was put together to give an estimator that would give very robust initial alignment on moving platforms. Because at the time the project was being sponsored by a company that was interested in developing a small consumer copter that would be hand carried and would be powered on while somebody was walking with it and waving it around in their hand, and also wanted a vehicle that, an estimator that could start up on moving platforms. So you could initialize a copter on the back of a small boat and then take it off, fly it around and land it again. And the EKF2 was developed to be able to do that, and also to be able to very quickly recover from an attitude disturbance. There's been a vulnerability that was introduced. If you spin it continuously at high rate around a vertical axis, it gets dizzy, it starts to wobble, and then if you stop spinning, it recovers. But if you don't stop spinning and you keep doing it and keep doing it, and then you switch back into a normal flight mode, the attitude error is going to be so large that the copter's scooting around the sky and you may not get time to recover. So, and that's something that a couple of our testers have run into. Other than that, it's doing good service with copter and plane. We're having very few issues coming up with it, and that's where what most people are using at the moment. EKF3 was started as a desire to try and achieve some commonality in the mathematics between the estimator, which had been developed for PX4 ECL library, and which is the default estimator for PX4 1.7. And it's got a couple of characteristics which make it useful for the new types of vehicles that we're starting to see, particularly VTOL vehicles that transition from a vertical to a horizontal flight attitude. Because EKF3, it estimates all 3 axes of accelerometer bias, which means that when you tilt over and go to vertical, go to horizontal, you don't end up with height offsets due to the fact that you've got an axis on the accelerometer that's aligned with gravity, which doesn't have a bias estimate for it. It doesn't do gyro scale factor estimation. That in practice, that turned out to be not particularly useful. The scale factors weren't very stable with temperature. So unless we calibrated the thing on a table or we controlled temperature pretty tightly, that wasn't a useful feature. It can handle higher yaw spin rates, and it's been the focus of the addition of new features. So we've got the ability to handle odometry data from a Z stereo camera. We can do range beacons, or the POS-YX beacons, which are actually UWB, which is the same technology as the UWB beacons, which hopefully will hit our stores sometime in the next 12 months. Is that right, Phil? Yeah, good. And then we've got an addition of wheel encoder fusion. So if you've got a little rover, it will basically do click counting on the wheels and use that to improve the navigation solution. And that's being used for people that are using those rovers and VTOLs and those types of platform types. And the rest, in terms of plane users, plane users are happy with EKF2, and most copter users are, unless they want to do high rate yaw spinning continuously, in which case I'd recommend that they probably consider using EKF3. Okay, so what have we added? Well, last 12 months, well, there was a feature that, when it's strictly speaking not an EKF feature, but it's to do with estimation, and it enables 2 or more GPS receivers to be put on the vehicle, and then if you by setting a parameter, you're able to blend the output from the receivers using a Bayes filter, which just uses the published accuracies for the GPSs and their position offsets, and comes up with a weighted blended average of the GPS receivers. It works beautifully for VTOL aircraft. You can put or in planes, you can put a receiver on each wingtip. You can put a receiver on the nose, so when you're vertical, it's pointing at the sky, and you've got another receiver on the wing, which points at the sky. When you're horizontal, and it just blends between the two. And the other thing is you don't have hard switching logic, which can cause problems with jumps. And I've used that for my own VTOL testing. I don't know if other users or developers have actually started using that feature. Then we've updated the EKF so that it better uses GPS to correct the barrow drift, and there's an option there to either use the GPS to correct the EKF's origin, the height of the EKF has an origin in latitude, longitude, and height, which is defined in WGS 84 coordinates, and that's the reference point for the flight, for the estimator. But when you're using barrow as your height source, what you're really measuring is a pressure attitude, and that can drift over flight. So as you get the barrow might change its temperature and drift, or the air pressure over longer duration missions can also change. And you can get 15, 20 metres of height change across a long duration fixed wing mission quite easily. So this feature enables the user to either decide, do I want to slowly adjust the height of the origin of the EKF to keep the barrow, the height consistent with the GPS, or do I want to adjust the output of the height, the actual published height relative to the origin? So I can either adjust my origin or I can adjust my height. And that's what that pull request enabled. It does mean, however, that if you switch, if you're on fixed wing and you're using EKF, which has got this feature enabled, and then you turn EKF off and switch back to DCM, and DCM is using the uncorrected height, you end up with a height jump. We've got GPS. We had another pull request when it was a minor one, and it was really for, we had some users that were doing flying and in an indoor environment where there was just enough GPS to pass the checks, but the receivers gets a lot of noise, and the vertical velocity on the receiver was really, really noisy, and it was actually, and indoors, you get 0.5 metre or 1 metre of height variation because the GPS vertical velocity was pulling the nav up and down, and that was causing unacceptable height variation. So there was a pull request that went in that enabled the vertical velocity use to be controlled externally. So depending on what flight mode you're in, it's an excessor that's provided. I don't think that's being used in master at the moment.
Not as far as I know, but
but I think we've got somebody who that wanted to use it for their code base, and they were happy for it to go in as an upstream feature. We've got wheel encoders. I think that's already working on Rover. Yep. That's okay. And there was a minor one with a script tool, Python tool, to assist with calibrating optical flow sensors. Okay, what have we got in the way of bug reports? Well, I think the first one's raised by Randy, and that is, at the moment, the EKF assumes that there are only a maximum of 2 rangefinders and doesn't handle more instances of rangefinders, but we've now got a rangefinder library that can handle up to, I don't know how many rangefinders lots. Is it?
Not sure.
Yeah.
4? I think it's 4.
Is it 4? Is it?
I think it's 4.
Yeah. All right. So we either, and this is an interfacing issue about how we what we actually present to the EKF in terms of those rangefinder instances. So that's something that would be good to coordinate on and get that sorted out. We got another one, which was a strange fault, and that was there's a range beacon simulator in Settle, and when they Settle beacon type, and they were getting floating point exceptions. Now, I latest upstream master, I checked, and I didn't get that particular bug when I reran that. So we may be able to close that issue. But I'd like somebody else to check to see if they can get it to, they can reproduce it on their system. And there's another issue which isn't logged in GitHub, which is if you're a plane and you take off and you have a really bad magnetometer and the EKF has to reset your yaw angle using the velocity, GPS velocity, and that reset happens after you've started using the airspeed sensor and you've built up a wind estimate. The initial wind estimate will be incorrect. You then reset the yaw angle. The wind states are wrong, and it then continues to reject the wind, the airspeed sensor, then for the rest of the flight. Right? So we need some logic in there to do the reset if that occurs. Now, if you look at the data, you can see that that's happened because there's a timeout flag that goes high, and then there's another measure of innovation consistency that will indicate that the airspeed fusion has failed. That's something that needs to be fixed. And we've got a couple of open pull requests. There are only minor issues. I think there was one publishing a cumulative change in yaw angle, as in, when you're fusing the magnetometer, how much is the magnetometer changing the yaw angle? Not on any given instance, but cumulatively over time, how much yaw angle change has been caused by the magnetometer fusion?
Yeah, that was for me for the compass learning.
Right, yes. Anyway, but the PR's still there. It's
Yeah, sorry.
I don't know how important it is. If it's useful or not. It's not useful, we'll just close it, or we can just open it. It's a low cost thing. Yeah.
It's something I still would like to do. It's for when we start moving the rest of the community across to doing no compass calibration at all and complete learning of compass states from scratch on, without any setup. And then I think this is going to be important.
Okay, so maybe it's something we pull in because it's low cost and it's just an external, an accessor. Yeah. And there was a minor one looking at improving stability of the covariance matrix, which is just another way of saying that there was some trying to improve the stability of the accelerometer bias estimates, and that's been sitting. And there were some negative test results, but they'd used a different parameter set, and I think that issue's that's still outstanding. But that was minor. That's a minor issue, and so I'm not in a rush on that one.
Paul?
Yes.
There's one also that's not necessarily EKF, but it's the high spin rate one.
Yeah, that was the one I talked about at the start. Yeah, it's a design characteristic of that mathematical formulation. The solution is use EKF3 at the moment. Now, if you're talking about the susceptibility to high spin rates, if you're talking about people that want to do rolling spinning airframes, as in we've got an open pull request at the moment, that's something, that pull request addresses the attitude, getting an attitude estimate, right? But it doesn't solve the navigation problem, right? But it's better than what we've got at the moment. To do I could change the EKF. The EKF could be reformula adjusted. The inputs could be adjusted to actually move the reference frame, have a body reference frame that's essentially in a D-spun axis system. So you essentially take your data and you transform it into a D-spun axis system, and then you do your navigation computations to the D-spun system. So you end up adding a second reference frame. You need an additional state, additional two states actually. You need to track the relative angular velocity of the two reference frames, the body frame and the D-spun frame, and also the relative angular position. So it adds an additional two states for the formulation. It's a fairly standard technique for can be applied for airframes that experience high rotation rates. It's not something, it's all doable, and it all takes time. It's a matter of prioritisation.
And just for scope, when we say high rotation rates, for example.
Well, for us, a high rotation rate, if you're rotating faster, what's the at the moment the IMU can go up to 2,000 degrees per second, right? Now we've got some we've got people with airframe concepts where they're like maple leaf, yeah, where they're spinning at 1,000 degrees per second or 1,500 degrees per second spin rate. So it's like 5 RPM, 3 to 5 RPM on an airframe. Yeah, 3 to 5 hertz. Sorry, not 5. Yeah. That'll be coffee, more coffee required. Yeah. Yeah, so 3 to 5 hertz, and it's a pretty fast spin rate. And at the moment, none of the open source estimators will handle that type of airframe. Now I know I've seen that there's a company. I don't think they use ArduPilot. I saw an airframe concept from a company, Iridium Dynamics, that had a spinning airframe concept, and they're going to have some challenges with the estimation side of things. But yeah, the techniques exist. We don't have to invent new mathematics for it, but it's a very specialised use case, and it's a significant amount of effort required to reformulate and recode to add additional states.
Oh,
Yes.
sorry. No compass, GPS bearing only. There's a P after that.
I didn't show up on my list of. Is that showing up as a
What was it?
on the EKF? Didn't see that as an
Using
open
multiple GPS for your estimate rather than
I've only got 2 open. I went through with open PRs and I only come up with 2 on GitHub. Is
Just
it?
tag it now and he's wrong. That's what I just did.
Where did you go?
Right. Oh, okay. So what we do have. Well, there's the use of GPS. Okay, yeah. So we've got that. Did they make it as far as a pull request? That was just a branch at the moment. Okay, here's a pull request. It may not have been raised as a pull request. All right. There is a branch that's been created, which enables you're from a GPS receiver, a more expensive GPS receiver, to be used as a surrogate for the compass. Branch is sitting there. I don't have the equipment to test it. Lead Grant, you have the
Yeah,
equipment
so that's
to
what we
test
need.
it.
So
Yeah.
now that rover's stabilised a bit more, we can tune it when Bob's having
Oh, okay,
so
yeah.
I can get back to it. But that code exists, so that's a compassless solution if you have an expensive GPS.
Right. Yeah. Anyway, the EKF side of things is finished on that, and it's
Yeah.
sitting in a branch.
Yeah.
And so what do? We just get some test data on it, and then we submit the PR.
I just mentioned in case anyone else is interested in that.
Yeah.
There's also the PR for compasses to say ensure that compass is actually healthy before putting it use for yaw. That one does relate to the EKF, so you have to make some patches for it, but that seems to have stalled out.
So you say that again?
AP Compass doesn't check that a compass is actually healthy before we use it for yaw. Healthy actually means that it's talking to us. So currently that can get past the EKF. So there's a patch to change that, and then you made some EKF patches, but that has stalled.
I wasn't tagged, didn't have an EKF tag on.
I've added it now.
Uh,
It did start. I've heard what I had to do.
Your talk's out of date, Paul. What are you doing?
You've got to move fast on this project. Yeah. All right, so we've got some planned EKF features, and some of them have actually they're already works in progress, as in there's code and there's some test data and things are happening. One of these is enabling multiple optical flow sensors in arbitrary directions. So you can have an upwards looking optical flow sensor. So if you want to fly a copter under a bridge or a large structure to do an inspection, for example, you could actually use the upwards looking optical flow to help give you a good position, particularly given that it's likely to be blocking your GPS. And that's been tested. The branch that that's in. Come on, links. I'm going to put the copy of this presentation. We'll send around a link to it, and I've got all the GitHub links embedded, so you'll be able to follow these up for yourself. Okay, it's put the presentation, it brought up the GitHub, but it's put it on a different screen. That's not very useful. Right.
That one's stuck on me. I think that one's waiting for me to test.
Okay, yeah. I mean, I did limited testing against my fence and under my my tilted door for my garage, and that's the extent of my testing so far. So it's not very rigorous, but it gave a stable position estimate. All right, and that's the hardware setup. So, a bit of 2x4 line, and we've got the Z stereo camera, which is doing some sort of looking at comparing quality of these different sensor types. That one's fitted with upwards looking optical flow, TX1 computer, vintage Pixhawk, and here GPS. That's it. And it doesn't fly very well. But you can throw it a long way.
Hardware issue.
Yeah. Now we've got some planned features, additional planned features. The next one, which is also a work in progress and it's proceeded to simulation, is an interface that consumes the output from either a monocular visual odometry or a monocular visual SLAM approach. SLAM being self-localization and mapping, and they're related technologies and they produce similar outputs, but they're not the same. SLAM uses actual features, so when it comes back round to a place it's previously visited, it's in theory able to reset its position and then correct for the drift, whereas odometry just continues to accumulate drift. The Adultery Algorithms are things like what's currently operating on OpenKai with the Z camera, which are much simpler computationally in terms of what you have to do for a full SLAM. So the input is essentially a position and an angle measurement for each camera frame. The challenge with the single camera or monocular based algorithms is, first of all, well, the axes are not NED. So you've got this position and attitude measurement relative to a world frame or an Earth frame that is got nothing to do with north, east, and down, and it drifts over time. And then the length scale is also unknown, because when you move forward, when you've only got a monocular camera, you know that you've moved a certain amount, but you don't know the distance to the object. So you have its relative movement, and the length scale is in some range. And the only way to determine what the length scale is to take that data, fuse it with IMU data, and then use state estimation to work back to, okay, so I moved forward and I realised that I've moved forward relative to the things around me, and now I know that I've moved forward by 0.5 metre instead of 5 centimetres. And that's one of the challenges with incorporating that type of output. So initially, there's been quite a bit of prototyping that's gone on with this. So we've already been through 3 standalone filters to try and estimate scale factor, 3 different derivations with different numbers of states for standalone filters. And none of them really, the problem is they worked well in isolation, but when you put them in the loop with the EKF, we ended up with a data dependency issue and some circular data dependency issues, and the estimate was not stable, and it didn't look like it was going to be a useful solution. So the fourth attempt was the one I've been avoiding, which was adding another state to EKF3 to take us to 25 states. So thank you, Chibios. And that has been, in simulation anyway, that's been more successful. So I can take off and using GPS as a surrogate, adding a rotation to it and an arbitrary scale factor, I'm able to take off in civil, put it into position mode, fly it around and land it just using the odometry data over that interface. So we have a prototype branch that's working there. I think when Kai gets his SLAM stuff going, then it's going to be really interesting to see how it works with real data. And then the next step is, once we understand the characteristics of that SLAM data, can we get something that simulates it in civil that provides representative sorts of errors and position jumps.
What are we doing? So, most of the time the SLAM system and, the EKF is running on different clocks, right?
Mm-hmm.
So, how are we syncing clocks? Because that is going to be an issue, right?
We have position measurements coming, over Mavlink that have, and they're time stamped on receipt. Now this is going to be an issue with faster rotation rates.
Yeah, and also the data the time we want is actually when the image was taken, right?
Yes, that's right.
Not processed and went through so much latency and those offsets are there. So is there a possibility to actually have time as a state and be estimating time as well?
I wouldn't do that.
We can do it separately.
But we could do it separately.
Yeah,
not in the EKF. So I wouldn't do it in the EKF, but we should certainly have a mechanism for maintaining essentially a clock drift rate and clock offset.
Yeah.
It's a simple two-state estimator running on each side of the
We've
interface.
got the code for that in the Canberra UAV system because we had that same problem with the camera coming Mavlink data in Canberra UAV. So we basically got a very simple little estimator that just uses the minimum time separation it's seen to be able to get the offset and estimate the offset for each packet.
Right.
We just need to move that into C++, make it a library, and then we can basically time correct the data before it goes to the EKF.
Right.
Okay, and this is an example of one of the simulations where we take off, and I've applied an arbitrary scale factor of 2 to the GPS data that's been used as a surrogate, and we take off and loiter, move it around. I'm typing, RC3, IC2 1000, RC2, manually typing into SL and bouncing the thing around. And each time you bounce it around and you change position, it progressively learns the scale factor. And then I just put it into RTL and bring it back. So that's a simulation. But that's with simulated data, which is all nice. It doesn't have other errors in it. So we'll see how it works in practice. And it's also worth pointing out, we're not using a scale factor directly as a state. We're using a natural log scale factor. So it's a logarithmic scale factor because of the amount of variation you can have in scale factor. If you get anything from a 0.1 to a 10, if you try to use a linear scale factor representation in the filter, it actually causes stability problems. Actually, we got, okay, what else have we got? This is one that Leonard would like. Wind estimation for multi-rotors. So the technique is that, without his permission, I'll grab his.
Permission granted.
So when we're in forward flight, there's the fact that you have to tilt to maintain speed means that you've got thrust force, which is which is tilted forward, and that's accelerating you in that direction. And then it accelerates until the drag, combination of drag on the rotors and drag on the body, builds up, and it's equal and opposite to the horizontal component of your thrust. So coppers have really got a drag coefficient, and you can think about drag coefficients fore and aft, and also they'll often have a different drag coefficient sideways. For example, a solo is more efficient flying forwards or backwards than it is flying sideways because of the amount of fuselage area. And it also depends on how fast you're travelling as well, and also on the mass distribution. We can use that bluff body drag characteristic, or the ratio of drag coefficient to mass, something called ballistic coefficient, and we can use that knowledge along with the measured accelerations to actually estimate the wind relative velocity, and fuse that in. And there's already an existing technique that's in service on PX4 upstream, and it's been used by a couple of commercial vehicles already, which enables those copters to do wind estimation. So that's the first step, and the wind estimate is useful for a whole bunch of different reasons. Mission planning, doing turn radiuses, all sorts of things that you can do with wind. The other thing that you can do with wind is you've got your wind speed, you've got your ground speed from the inertial nav system. You can then work out, this is my airspeed. Once you've got airspeed, we can compensate for the effect that with most multi-rotors, depending on which direction they're flying, because of the flow over the body and the openings in the body, depending on which direction you fly, it actually causes a static pressure offset inside the body, which means that you'll see them fly forward, and in many cases they'll dip and slowly drop as they go into forward flight, and then you come to a stop, and then they'll slowly rise up over like a 5-second time constant. And that's not the control loop's doing it, as much as we'd like to blame the control loops. It's not me. It's not him. It's not Leonard. It's actually
Hardware problem.
it's a hardware problem. It's hard to tell. It's a hardware problem. Yeah. Not compensated for in software.
Yeah.
But because what we do in software is we fix hardware's deficiencies. Is what we can do, if we know that there's what that coefficient is, and if we know how much of the dynamic pressure, which is a half rho v squared, half times density times speed squared, what fraction of that is being seen by the barrow, either as positive or negative offset, and we can represent that sensitivity as like an ellipse around the vehicle, and we know the airspeed and the direction, we can actually compensate for it. So unless you've got a really strange shape that's very asymmetric, it actually provides you, with tuning, it can provide a very useful compensation for that effect, and you can do fast acceleration and stop manoeuvres without any of the sort of bob up or bob down at the end.
Did you get to check to see whether the kinematically correct altitude estimations have gone in or not?
They're not in there. In the
Because that's the other exacerbating factor of that, is the way that interacts with the EKF, the velocity estimates.
that actually works. Actually, the fact that the EKF doesn't drop the height, the testing that I've done, not on ArduPilot, but on PX4, indicates that a kinematically consistent output performs worse in forward flight height tracking than the existing output does. Because the height is being pulled down. So when the estimator sees the barrow pulling down, it says, well, I've got a height error. So it starts adjusting the height, but it doesn't adjust the vertical velocity. And same thing at the end. So it actually slows down. It slows down how fast the copter is responding to that error. If you go for a kinematically consistent vertical velocity, one that's kinematically consistent with the vertical position, then the copter will respond to that error faster.
We'd have to get those logs out again, but those logs that I was sending you, the height tracking, the height error was caused predominantly by the velocity.
Well, that's why you don't want the kinematically consistent velocity, because when you're getting these barrow disturbances, the normal velocity, vertical velocity state estimate is more stable and more resistant to barrow disturbances than the derivative of the height estimate.
If that wasn't what we were seeing in those lots of the velocity error was causing the altitude offset as opposed to the...
All I can do is say what I've seen in what I've seen in the testing in the last 12 months.
Yeah.
Okay.
Yeah, we'll have to see if we can reproduce that again.
Okay, and then we come down to potential features. These are features which haven't started. There is no sponsor for these features at the moment, but essentially I'm ticking along as a background R&D task because it's longer term. It's something which I think is important because I don't like magnetometers. I see too many here. Look at this flight log. What's going on? And it's caused by problems with magnetometers. And not so much for planes, because planes have got the ability, you detect your takeoff, you work on the basis that it's probably flying pointy end forward at the point where it's launched or takes off. If it's not, then there are other problems. But with anything that takes off vertically, if you take off with a bad yaw angle, 90 degrees, 135, 180 degrees out in yaw angle, the inertial nav solution, as the copter starts to move, the initial nav solution will say, well, you're accelerating in the north direction, but it's actually accelerating south. The position of velocity loops then put in a tilt correction, which is now in the opposite direction of what it needs to be, and the thing just rapidly accelerates away. Now, what we have to counteract that is we have the EKF failsafe that kicks in, and it's been stopping ArduCopters, copter flyaways for a few years now. And it does stop a flyaway. It doesn't necessarily stop a crash though. So if you're taking off near adjacent objects, by the time the failsafe kicks in, that's when it's into the tree, on the side of the building. So we would really like to have a method of independently checking the yaw and much more rapidly determining what's the actual yaw angle and doing it quickly. Now the problem with the EKF doing it is that the EKF's got a single yaw estimate. And to get that single yaw estimate dragged around from 180 degrees in the wrong direction through to be in place enough so that it's safe for flight takes quite a bit of input data and a significant amount of time, more time than you've got. So I have a former colleague and PhD candidate, Dr. Adultery, and she'd been helping me with setting up with MATLAB scripting to do some comparisons on different versions of an estimator. Something that's simple, not too many states that can run separate to the EKF, and it has one job to do, very rapidly form an estimate on yaw angle. And we compared a number of techniques, EKF, UKF, and then what we call Gaussian sum filters, which run essentially a bank of EKFs, or a bank of estimators, and then use their statistical representations of the data to combine the data together to actually produce, this is the most likely yaw angle. And then something called a particle filter, which is where you have a whole bunch of different initial yaw angles and you just propagate all those particles forward in time. And these are standard estimation techniques that are used for, the last three techniques tend to be used for target tracking problems, not so much, they haven't been used traditionally for navigation problems in the past, but for this particular problem, they seem to be a useful method. So, and it appears, just on preliminary analysis, that the Gaussian sum filter with running a bank of EKFs gives a good performance to computational cost ratio. So here's what happens with the EKF. So we've started, and on the bottom here, we have we essentially have, this is yaw angle. Apologise, this was, came off the press pretty late and I haven't added the axes to the graphs, so sorry about that. But we have yaw angle. Red is the truth yaw angle for this particular set of simulated data. And above we've got north and east position. So this is a simulated vehicle that basically accelerates and does a few position and yaw changes. And then we have the estimated yaw angle. And it starts off 180 degrees incorrect yaw, and then we run it through the EKF algorithm. And you can see it struggles, and then it gives up, stops using the data, and then it takes a long time to fully recover its yaw angle.
It's in radians vertical axis.
It's in radians vertical axis, and that's not particularly, and that's not a useful result. The recovery time is too long. However, if we run the Gaussian sum filter, it's wrong. As soon as the vehicle starts to accelerate, which is at the 5-second mark, the inconsistency between the GPS data and the IMU data becomes observable, and then it collapses in or converges into the correct yaw angle within 2 seconds. Now, if we can get, even if we can get 3 or 4 seconds on a copter to recover from a very large yaw angle error, that's enough to prevent the great majority of crashes.
So this is running separately from the main state
Yes.
estimator.
Yes,
So we can run this in a separate thread,
Yes.
so it doesn't have the time slicing issue, and basically have this as a background estimator. How does it then feed that correction
Well,
back?
because the EKF will be desperately unhappy at this stage.
Yep.
Because it's seeing massive inconsistencies. So then, if it gets to the point where it goes, oh, I'm rejecting GPS data, and it goes across to and this Gaussian sum filter returns and says, hey, I've got an estimate. My estimate's good. I've converged.
Yep.
Then the EKF will go, okay, well, I'll take yours. I'll just do your reset.
And how many elements in the bank, how much memory per element in the bank?
It's a 3-state filter. How many energies? 1, 2, 3, 4.
So matrix
20.
9, 3 by 3.
We had 20. This was just running 20 on a bank, but they're
Yep.
3-state filters. They're very,
So
very
nine floats, so 36 bytes. So 20 of them, so 720 bytes.
Yes, it's not accessible.
Oh, that's
memory.
cheap.
Yeah.
Yep. And the computational cost of each element of the bank?
Oh, I haven't
Less than
assessed
our
that.
current filter, presumably,
Oh, yeah.
for each one.
Oh no, but each one is tiny.
Tiny.
It's a bit like the filter. You know the filter that we used to run on the old APM to do airspeed calibration.
Yep.
It's equivalent to
very
that.
cheap.
Very cheap.
Very cheap. So we put this in another thread and basically leave it running permanently, soak stuff up, and then the EKF would call to it and say, you got something for me? You got some correction? Or is it going to push into the EKF and say,
No, I think
reset now?
it will provide. Here's my estimate. Do you want to use it?
Right.
We wouldn't push in because if you look at the EKF's happy and it's not rejecting GPS data and those innovations are good.
Yep.
Then there's no reason to do your reset from this filter.
Yep.
And look, and then we can evaluate it over time and see, it does it end up being more reliable, or is it one of these things that gives you a very quick, rough estimate to just keep you flying again?
This is really exciting.
Yeah,
It's
it really is.
fantastic.
I've got
Yeah.
a perfect test for that.
Can I ask, work with other forms of position input? Like for example, like rovers always have a problem. They're driving around on metal floors or something, the metal environment, but they might not be using GPS. They might be using wheeling colors. What do you use?
Well,
for that as well?
yes, you could use it because this is using GPS velocity, but we could just as easily reformulate that little 3-state filter to use a velocity, a body frame velocity in the XY direction, as in you assume your lateral velocity is 0 and your forward velocity is whatever it is for the encoders.
Yeah.
So yes, we can do that as well.
Flow data?
But if you do that, it's only relative to some arbitrary frame. So the problem with your angle without GPS is you can get a your angle, but you don't know what it's relative to. It's an arbitrary reference. It's a reference to where you started from.
Yep.
So flow data?
Flow data at all useful for this?
No, I'll take, well, not directly, but where flow data is useful is flow, and it buys you time.
Hmm.
So
Yeah,
we can do
yeah.
that in flow rather than the position loops, accelerating the thing away and trying to correct it in the north direction instead it's flying south. With the flow data, you basically, it might drift around a bit, but it's
Yeah, it's not going to fly off.
yeah.
Yeah.
So if this is simulated data and we don't know, how well this is going to work in practice when we get some real flight data. So the next step is to get some log data from a flight and then run it through the filter.
We can fly this afternoon.
Yeah, put somebody can put their vehicle up with a 180-degree compass error, and let's see how it goes.
So that I was going
What could possibly go wrong? Yeah,
Oh,
Sky-
Volunteer. Sure, the skydiver.
Sorry.
I recently had one of my fast vehicle tests was taking off on a place where there was some pipes underneath the ground, and I was getting that 90-degree yaw offset, and so the thing was going that way when I was going that way, and it was getting 100 metres out at 120 kilometres an hour and doing an EKF.
I'll say.
Yeah,
But it travels a bit of distance before that kicks in.
yeah, and then but that would be a perfect test for this.
That's brilliant. So that's it. That's the state of the EKF.